Looking back to its origins in the late 1960s and early 1970s, how do you think FFF has evolved in terms of instrumentation, applications, and theoretical understanding? And then which of these advances do you see as having had the biggest impact on its uptake in academia and industry?
I think there is a lot that has changed. I wasn't personally there in the 60s and the 70s, but I do have memories even 15 years ago of handmade channels um, and cutouts that we customized in the lab and initial concepts of commercial channels that were not there yet. And at the time, a lot of FFF analysis was done in the research labs. And a big deal was making FFF work and then performing analysis on it. So it was very lab dependent. But it was extremely challenging and also extremely exciting because then you had your own equipment. And what happens over time is that a lot of automation, a lot of efforts into compatibility with HPLC came out. So at that point, it became extremely easy to make, even just build a channel. We used to screw them by hand and cut the plastic sheets with scissors in the lab. And then you can just buy them. You still have to assemble that, but it takes a very short time. So you have something that is more, it has more the commercial feel, and that makes you feel better about the reproducibility and the reliability of it all, and also makes it easier to compare what you do with what your colleagues do, and therefore you build more reproducible science because the principle was interesting and clear, but how hardware and how the subjective way of making things was impacting the results that was not too clear. And that was a problem. And of course, it also depends on the theoretical understanding because there is a lot of history on what are the mechanisms that actually take place in FFF separation. And of course, when we talk about FFF, we can talk about gravitational FFF, we can talk about asymmetrical flow, field flow fractionation, or AF4, which is the most established technique. We can talk about different forces that develop separation. The different range of samples and sample size that you can analyze also are subject to different mechanisms. So I really believe that the expansion and the understanding of what you're actually seeing and what you're actually impacting in terms of sample size and sample properties really drove the understanding and the customization of the sample rather than the technique. You know what you can do with FFF and you know whether your set of samples can be analyzed in a way. While at the beginning, it was more like, let's explore all that can be done with it. And let's try to understand why it happens in this way.
Yeah, I agree, and I think that I mean the absolute most important thing was, of course, the introduction of commercial instruments, because I started out on home build AF4 equipment, and when it worked, you had to really go for it because you never know when it will stop working, right? So I mean, to have something broadly accepted in both in academia and industry, of course, this is completely unsustainable. So I think that's very important. Then, of course, coupling it to light scattering, multi-angle light scattering, that's also absolutely crucial for expanding the applications. And then I think it was mainly just a matter of time when it would find its way into different types of applications. I mean, certainly the instrument manufacturers drove that in specific ways where they saw market opportunities. But yeah, I think that the development of the commercial instruments and coupling to light scattering was really a game changer for FFF and certainly for A4.
Which emerging application areas do you expect to be the main drivers of the next stage of development for FFF?
So I do think that there will be a big venture basically from the research applications to pharmaceutical and real life applications, and that especially biopharma will be one of the strongest drivers here for the future of AF4. because we're also looking at the moment at much more modern and more complex pharmaceutical samples. For example, there's like AAVs where they can be loaded or they can be empty and they need to be analyzed. What was established that it works very well with AF4 in combination and with multi-angle light scattering. We're talking about lipid nanoparticle molecules that have very large size distributions, more delicate samples like extracellular vesicles. And there's just a lot of samples that are hard to control because they're prone to aggregation. But basically that heterogeneity then affects directly like the efficacy and the safety of your sample. And so there, I think that AF4 will enable basically the separation of those populations and can then link the size directly to aggregation states and also structural data in one experiment, what should help with quality control or, for example, formulation efforts for novel therapies. And there's still, there's still a lot of things needed to make it fully implemented in biopharma. I think there's a need for like automated method development and standardization and to make the method more accessible to biopharma. But I do see that FFF here can help answer questions that are very relevant for the field and where FFF can also then support decision making and improving or controlling processes, parameters, and also product quality.
Also, I want to add another field which I think is very important for the future, and this is environmental and also nanoplastics analysis. Yeah, we all know that it's not a question of presence or existence. It's everywhere, nanoplastics, and we now need to find out in which size fractions, or also what's the chemical composition, or also what's the relevance with regard to exposure. And this is not limited also to environmental samples. It can be transferred also, or it's very relevant also for food, beverage, consumer products, how it's been tested actually also for the microplastics. And I think there in this field, AF4, in combination with, of course, a good detection system, like, for example, ICP-MS or pyrolysis, GCMS, Raman spectroscopy, allows a size resolved, but also a chemical information delivery. So it's not just averages that we get. And I think this is very important. But we have to be careful because also the sample preparation is essential, especially when you have a complex mixture. And there, of course, we all know measuring standard materials is quite easy. But if it goes to the real world, then we have much more than just one particle in the solution. And this makes it, I could think, quite challenging. Also, low concentrations and interferences need to be considered in that field. Coupling other techniques, like as I mentioned, ICP-MS, but also scattering methods like X-ray or also neutron scattering, allows a much deeper insight into the structures. So we can see now structural levels of molecules which were not visible before. And I think in the future, so maybe in 5 or 10 years, also other advanced spectroscopy methods can be coupled to FFF to get a size resolved information about the structure. Or maybe microfluidic bioassays could be coupled. But I think, of course, always is in combination with robustness and reproducibility. And this is a big point that has to be considered in coupling advanced detection systems to FFF.